probably equivalent to a uniform algorithm.
Okay, it looks like it's time to get started. I'm very happy to introduce Sandra Kiefer, who's going to talk about combinatorial properties of the Weisfeiler-Leman algorithm. Sandra.
Thank you very much. As Neil said, I'm going to present you some combinatorial results on the Weisfeiler-Leman algorithm and also the equivalent formulations in logics. The results treat ways to measure the power and the complexity of the algorithm, so they might eventually be helpful in order to approach graph isomorphism. As a reminder, the problem to decide whether two given graphs are isomorphic or not is in the complexity class NP, but its precise complexity remains open. In particular, it's not known whether it's in the class P. In his breakthrough result from last year, Babai got to show, after decades of research, that it can actually be solved in quasi-polynomial time. And in his proof, he heavily relies on a polylogarithmic dimensional variant of the algorithm, of the Weisfeiler-Leman algorithm. So yeah, it's not only in his proof, but basically in all approaches, theoretical and practical approaches to tame graph isomorphism, a very indispensable subroutine. How does the algorithm work? So the algorithm iteratively refines a coloring of the vertices of the given graph, or of the given graph. More precisely, the k-dimensional variant computes a coloring of the k-tuples of the vertices in iterations. So the one-dimensional algorithm, which is also called color refinement, computes a coloring of the vertices themselves. And how does it do it? In the refinement step, which is the step that is applied repeatedly, two vertices that had the same color before now get different colors if there is a color so that they have a different number of neighbors in this color. And this is applied until the induced partition doesn't change anymore, then we call the coloring stable, and this is actually what the algorithm returns. And why it's useful for graph isomorphism is because if you have two graphs and they result in non-isomorphic stable colorings with respect to any dimension of the Weisfeiler-Leman algorithm, then these graphs are non-isomorphic. So therefore they can be used in applications to decide graph isomorphism. But by the Seyfert-Riemann construction, no dimension of the algorithm actually suffices to decide graph isomorphism by itself. So it can only be used as a tool, but not as the only tool. The inverse is not true. So there are graphs which are non-isomorphic but have non-isomorphic stable coloring. So you would need something more. You can only use it as a subroutine, and that's how it's used. So if you want to use it as a subroutine, sooner or later you basically get to two main questions, which I'm going to treat here. So the first one is, what is the power of the algorithm? So for which graphs does it actually suffice to only use the algorithm to apply graph isomorphism? So for which graphs can you apply the algorithm and decide only based on the stable colorings whether they are isomorphic or not? And by the famous correspondence to logics, this actually is equivalent to definability in the logic CK. So first order logic with counting and restricted to k variables. Yeah, that's the first question. And the second question is everything that has to do with the complexity of this algorithm, because you want to have the complexity of your complete algorithm. And here in my talk, we are basically focusing on the iteration number of the algorithm, because that's actually what's important when you want to parallelize the algorithm. And this iteration number also has a correspondence in logics. It is the quantifier depth, the quantifier rank in CK logic. Okay, so I'll start with the power. Let's go back to the one-dimensional algorithm. We have seen that it computes a stable coloring of the vertices. And the stable coloring that color refinement, so the one-dimensional variant computes, is the coarsest, or induces the coarsest equitable partition of the graph, which means that it's the coarsest partition such that it is regular in each class. So for example, in this blue class here, the blue class here is 2 regular in itself, because every vertex in the blue class has degree 2 within the blue class, and regular from both sides between every pair of classes. So here from this class to this class, it is 2 regular, and from the other side it's 1 regular. So yeah, about the power, if you have 2 graphs and they have isomorphic stable colorings with respect to some dimension of the algorithm, then this dimension cannot distinguish them, and therefore they are called equivalent. So in color refinement, it's color refinement equivalent. And we say that a graph is identified by color refinement if every equivalent graph is isomorphic to the graph. So if it suffices to apply color refinement. Unfortunately, as I said, not every graph is identified by color refinement, so here are 2 simple examples. If you apply the algorithm, you will quickly see that they are equivalent with respect to color refinement, but of course they're non-isomorphic. So this cycle, the 6th cycle, is not identified, because there's a non-isomorphic one which is equivalent. As to cycle lengths, what is maybe interesting is that the 3 cycle, for example, and the 5 cycle, so cycle of length 3 and of 5, they are identified. So, and also it is known that all trees are identified by color refinement already. And now this leads us to the questions, which are the graphs that are identified? And yeah, Pascal Schweitzer and Erkal Sellmann and me, we found a complete characterization in the way, meaning that this is not only a compact description of these graphs, but it also yields a way to decide quickly whether a given graph is identified or not. So the theorem is that it's identified if it flips to a big bouquet forest, and this has the correspondence in logics that it's definable in the logic C2 if it flips to a bouquet forest. I would like to present the proof here, but I'm going to present another proof for something else. So let me just give you the tools to understand the theorem. So I'm going to explain what a bouquet forest is and what a flip is. So you obtain a bouquet by taking 5 copies of a tree with some designated vertex. So here you have 1, 2, 3, 4, 5 trees, and they all have equivalent or the same designated vertex. You bind these trees together via a 5 cycle on these vertices, and you obtain something that looks like a bouquet. That's why we called it like this. And then from this you can construct bouquet forests as by taking the disjoint union of any type of vertex colored trees. So everything that doesn't contain a cycle here is a tree, and you can have isomorphic ones and non-isomorphic ones, whatever you want, and then also non-isomorphic vertex-colored bouquets. So everything that you see here is one bouquet forest. And for example, these here would be isomorphic if you didn't consider the colors. So there's no color-preserving isomorphism, so that's okay. And actually, this non-isomorphism is crucial in the proof, so that's why we included it in the definition. Okay. So and the theorem also included some type of flipping. I'm also going to explain this. You obtain the flip of a graph by computing first the partition that color refinement induces. So here you have it. And then you consider every pair of color classes, also a color class with itself, and you flip in it, meaning you consider the class and the edges running within the class and the complement. So here you have the 4 cycle, and the complement would contain only the diagonals. And if the complement has less edges, so here it's 2 edges versus 4 edges, then you replace them. So here you only take the diagonals. You do this within every class and between every pair of classes. So here there are 2 edges, the complement has no edges, so you replace them, and that's the flip. So the goal is to obtain a graph that has, in a way, few edges. And why this is allowed is because of this lemma, that a graph is identified if and only if its flip is identified. So that allowed us to restrict ourselves in the analysis to graphs that have few edges. Okay, so with some other combinatorial ingredients, we obtained this theorem, and we could also generalize it to finite relational structures, obtaining also a complete compact characterization for them. But the thing is, this characterization for general finite relational structures was only possible or nice because the color classes in them, the vertex color classes in them, are either trivially identified, or they are one of 8 peculiar looking cases. So we only have these 8 types of exceptions. And the problem is that if you want to generalize this to higher dimensional variants of the algorithm, they would not look that nice, and there would also be infinitely many. So yeah, the strongly irregular graphs are included there, and therefore you cannot really expect to obtain a nice characterization for them. Okay, now I'm going to talk about the complexity, and since I'm basically going to present results about the 2-dimensional algorithm, let's quickly see how it works. So the 2-dimensional algorithm colors 2 tuples, meaning the arcs of the graph, and in the beginning they are colored according to whether they are an edge, a non-edge, or a loop in the graph. Every arc has a color, so in a sense it is complete. And then in the refinement step, they get different colors if they had different colors before, so it's a refinement. Or if these multisets don't match. Don't focus on them too much. We're going to look at an example, and then this is applied repeatedly until it's stable. So I'm going to explain these multisets here. So suppose this is the graph. I mean, it's not complete, but these are edges in the graph, and you want to recolor, or you want to compute the new color of the edge between the vertices 1 and 2. Then the new color contains, it's a tuple, and it contains as a first component the color of the edge that it had before, so yellow. And as a second component, it's this multiset. And the multiset is actually computed by looking at every third vertex in the graph, also the vertices 1 and 2 themselves, and the triangles that this vertex forms with 1 and 2. So for example, if you take the vertex 5, then it forms a green V with the vertices 1 and 2. So it's one of this. And then you have the same for 6 and 9. So it's 3 times this one. And you do this for every other vertex in the graph, and you obtain a multiset looking like this. And this whole thing is the new color. So I also had an example of a simulation of the algorithm, but I deleted it because I thought I wouldn't have enough time. So what you have to remember of the algorithm is basically that it computes colors of the arcs, and it does that based on the triangles that this arc forms in the graph with the other vertices.
So in the future, instead of deleting it, put it at the end in the period of time.
Sorry?
In the future, just put it at the end.
Yeah, I have other stuff at the end.
Okay.
Yeah. No, it's not so important. I mean, basically, you just have to have the idea of these triangles. That's, yeah. Okay. So what's known about the complexity is that the stable partition of this algorithm, the k-dimensional variant, can be computed in time n to the k plus 1 log n, where n is the size of the graph, the number of vertices. But as I said, if you want to parallelize the algorithm or want to obtain bounds on the quantifier depth of the corresponding formulas, you actually need to look at the iteration number. And here's a table that summarizes the known results. So some of them were already presented by Christoph yesterday. I'm just going to recall them. So this bound for color refinement, the 1-dimensional variant, was obtained by Krebs and Verbitsky. They actually constructed a tricky graph on which the algorithm needs this number of iterations to stabilize. And then for also color refinement, the trivial upper bound n-1, for some n it's tight, but so far we have not really understood the structure behind this. I mean, we have found 4 or 5 n's for which it's tight, but there doesn't seem to be a real possibility to generalize this. And then as to lower bounds, it's only known that the lower bound is linear, and it was proven by Führer in 2001 using graphs of bounded color class size. This will be important later on. And yeah, yesterday Christoph presented a new lower bound for finite structures. So this is only about graphs. And in our understanding, if you see this new lower bound and compare it to the trivial upper bound, so that's the number of times you can partition a set of n elements, you can refine a partition of a set of n elements, then you might suspect that actually this is also tight. But yeah, what we prove is that it's not the case, at least not for k equals 2. Yeah. The thing is, yeah, you might want to know tight or better upper bounds for larger dimensions of k, but actually it was really involved already for the case k equals 2, so we restricted ourselves to this case. What we could show, Pascal and I, is that the number of iterations of this algorithm on graphs of size n is at most n squared divided by log n. So yeah, we have this new log n here, and you can translate this to logics by the correspondence that which states that in the logic C3, formulas for graphs on n vertices require only this quantifier depth. And you do not see this now, but the way we have proven it actually shows that if you have graphs of bounded color class size by this lemma, then the upper bound is linear. So it's O of n when t is fixed. And therefore, for graphs of bounded color class size, the upper bound and the lower bound proven by Führer, they match up to a constant factor.
Excuse me, these color classes, these are the colors obtained by the algorithm. So you are bounding.
The color class sizes are actually so it's the vertex color class. No, it's all color class sizes, but all the sizes that appear within the algorithm. I mean, they get smaller by the time, but so basically it's the sizes with which you start.
In the end, the sizes in the end of the algorithm.
No, at the beginning and in the end. I mean, yeah, but in the end they get smaller. So, yeah. Okay, so how did we prove this theorem? Actually, we defined a game on the graph, which might seem a bit surprising, but the game allowed us to decouple the dependencies between the processes that the algorithm causes, so that we don't understand that we have two players, and one of them has the role of what we don't understand from the algorithm, and the other one has the role of what we can control. So we have two players, Maxi and Mini, and they play on the graph, meaning they refine the coloring of the graph they get and return this graph with a new coloring to the other player. And they do this according to some rules which relate the game to the Weisfeiler-Leman algorithm. The details are not important here. So yeah, they refine the edge coloring of the graph they are given, they return a new colored graph to the other player, and they continue until you get the discrete partition. And all these turns contribute to a common total cost of the game. And we could show that this total cost forms an upper bound on the iteration number. So the player Maxi wants to maximize the total cost, and Mini wants to minimize them. So in order to obtain an upper bound on the iteration number, the challenge was to provide a sufficiently good strategy for the player Mini, because it's an upper bound, and then you have at most this duration of the game. And how we found it was we distinguished between large and small vertex color classes in the graph. And for the large classes, we used a potential function, which I'm skipping here, so I'm only going to have a look at the small vertex color classes. And for this, so the idea was we wanted to find a strategy for Mini. And for this, we let her construct auxiliary graphs on which she makes some computations, and then she uses this result to obtain or to know what moves she should do on the original graph, on the graph that she's playing on. And I'm going to illustrate this here. So here, so it's all about the small vertex color classes. You have three small vertex color classes, C1, C2, C3, blue, green, red. And so this is a part of the graph that they're playing on. And if you have this set, the subset of C2, is exactly the neighborhood of this set in the original graph, then in the auxiliary graph, you draw an edge, you insert an edge between a vertex corresponding to C1, M1 and one to C2, M2. So this edge means this relation in the original graph. And then if you have the same on the other side, so this is also exactly the neighborhood of M3 with respect to some colors, then you have this edge. So in the auxiliary graph, you have no edge colors, and you also have no I also omitted directions here, but the auxiliary graph is undirected and with uncolored edges. And then so Minnie computes this auxiliary graph, and if you have this relation in the original graph, then actually, according to the rules she's allowed to use to make her moves, recoloring all the edges between M1 and M3 is a legal move for her. So I haven't explained what her rules are, but if this is how the situation is, then she is allowed to recolor these edges. And you account for this in the auxiliary graph by inserting this edge. So by completing this triangle. So there are 3 types of these triangle completions in the auxiliary graph, and all of them correspond to legal moves for Minnie in the original graph. So what she does is, this is her strategy, she gets a colored graph from Maxi, and she's going to return another graph with a finer edge coloring, arc coloring. And she does this by first cleaning up the graph, which means she accounts for some consistency in the edge colors. So yeah, this is not really important for us now, it's just a technical detail. When she has cleaned it up, she computes the auxiliary graph of the graph she has, so this one, and she checks if the auxiliary graph still allows triangle completions. So if the triangle completions of the auxiliary graph are not the auxiliary graph itself. So if these edges are missing somewhere. And if this is the case, she performs one iteration of the Weisfeiler-Leman algorithm on the graph and accounts for these triangle completions. So one can show that if she computes one iteration and again computes the auxiliary graph, then she has completed all the triangles from before. And she cleans it up again. And then she checks if there are more triangle completions now possible. If there are, she does this until there are no more triangle completions possible. And this is the graph that she returns. So what we could show is that following this strategy, she only causes extra costs of 2 to the t of n, where n is the bound on the size of the small color classes. And actually, maybe it's interesting to you, this term results from the number of vertices the auxiliary graph has. So as I said, the auxiliary graph has as vertices tuples of a set and a subset, where the set is always a small vertex color class. So this is a bound on the number of vertices you can have, and actually from there you get this total bound. So this is the bound that you have for the small vertex color classes. And yeah, I didn't explain the large vertex color classes, but from them, using this potential function, you get this bound. So all in all, you have a total cost of this, the small ones and the large ones. And then where t, as I said, where t is the maximum size of a small vertex color class. So you have to adjust t so that this gets optimal. And you can do this by setting it to log n divided by 2, and then you get the bound I mentioned. Yeah, if you just insert log n divided by 2, you get this bound. And yeah, also the bound for the logical quantifier depth. So this is a corollary from the theorem, but if you examine our proof carefully, you can see that we actually didn't use counting anywhere. It seems kind of surprising. Also, in the case of large color classes, at first it looks like we're actually counting a lot, but in the end we only needed existence, so we can omit the counting here, and we can replace also C3 by L3, so the logic without counting. Okay, I've reached my summary. So yeah, I was going to talk also about open questions. So what have we done? For the identification in dimension 1, we have given a complete characterization. That's nice, and also for relational structures. So this, I would consider this solved. But what about the identification in higher dimensions? As I said, not only with our method, but also because of this problem with the strongly irregular graphs, you cannot really expect to obtain a characterization in any way, a nice characterization, as I said. So this is not very promising. Then as to the complexity, we have found new lower bounds for the iteration number in dimension 2, so for the 2-dimensional Weisfeiler-Leman algorithm. So you can still try to improve them, but this is at least a progress. Yeah. as to the iteration number in higher dimensions, we have not yet found new bounds, but it is possible that you might generalize our constructions. I mean, it's not straightforward, and so far we don't know how to do this, but at least it might be possible. And then another thing you might want to try is to find bounds on the iteration number for finite relational structures. Actually, we think that this is possible using our construction, so you can just adapt it a little bit and it will work for finite relational structures, but we have not done it so far. Thank you.
We have time for questions. So,
Well, you didn't tell much about this initial coloring. What's the initial coloring? Well, can be. What kind of color?
Anything. So that's something that's the input. You get a graph with any coloring.
Okay, but
And-
then expressibility, does it depend on the initial coloring in any way? Say I give you initial coloring where every vertex has a unique color.
then you're done.
Then you're done.
Then you're
exactly.
done, yeah.
So then expressibility is just perfect. But it's probably not what we're interested in.
Right, let me go back.
Expressibility, but you have to identify that twice a month.
Yeah. Anyways.
I think, but looking at graph isomorphism, in some cases, some of the vertices are obviously in small groups. So it's a restricted problem that's interesting. That's sort of small color class. And the general problem has large color class, like the whole graph.
Yeah, well, that's fine. Well, the question is, well, depending on what initial coloring is, does the sort of, power of this algorithm changes? That's
I think, so this result is from a year ago. I think, as far as I remember, the theorem is about uncolored graphs. And you can show that if a graph is identified, all vertex-colored versions of it are also identified, but only by color refinement. This is not true in higher dimensions. So the theorem holds for uncolored graphs. You have an input which has no colors, and then the theorem holds. And we also have another theorem stating that for color refinement, if the graph is identified, then every vertex-colored version is also identified. So, yeah. So basically, you can go back to the uncolored version and check it for this one.
okay. I'm probably missing something. We better talk on offline.
Is another question? So I have a question for
Yeah.
when you say, okay, you can characterize, what graphs are, you can tell what graphs are characterized with one-dimensional.
Yeah.
And then two-dimensional, it's messy already.
Yeah.
Which suggests to me a little bit, let's add something to the logic to make it less messy. I don't know if that hints you towards anything. This is
Okay, yeah. I mean, usually my perspective is not the logic's perspective. So, but yeah, maybe.
or to the
I mean,
other,
yeah, maybe
if
you can do
want to
this.
something else that would get rid of your messy stuff.
Yeah.
I'd like to know what it is. Yeah.
I mean, also the case of color refinement seems kind of special because of this, what I just mentioned, that if a graph is identified, every vertex-colored version is also identified. And there is another result which only holds about which only holds about color refinement. So, yeah, this just seems a very specific, nice dimension in a way. But yeah, maybe, yeah.
For sure. There was another comment.
Yeah.
Yeah, I had a similar kind of question. So if you do this where you're only counting 0 and 1, so that this is like characterization in a modal logic.
Mm-hmm.
So it's known that if you add a star operator, like transitive closure,
Mm-hmm.
then you characterize every finite structure.
Okay.
So if you had something like that, you could hope to do this.
Okay.
Because this corresponds to like modal logic with counting
Okay.
quantifiers.
Thank you.
Okay. So thank you very much.